Hi, my name is Kent Lee, and I teach computer science at Luther College. In this series of lectures, I'm going to introduce you to the implementation and use of various programming languages. More importantly, I'm going to talk about three different paradigms of programming, three different ways of thinking about programming. The imperative object-oriented, which you may have encountered before, the functional paradigm, and the logic paradigm of programming. All of these topics are covered in more detail in my textbook, Foundations of Programming Languages. I would encourage you to buy that text and use it along with these lectures to get the most out of this material. To start, we're going to look a little bit at the history of programming languages and understand a little bit where the motivation for programming languages comes from. I have an accompanying website for this text. You can see the address right up there that you can use. It has some of the pictures or figures from the text and some of the practice problems from the text. The practice problems, the solutions to them are available in the textbook, so you can do the practice problems and get some feedback right away on whether you understand some of the material or not. And there's a lot of supporting resources for this text as well, including a virtual machine, a compiler, and a type inference system that we'll be looking at as we work our way through the text and through the material covered in the text. So I'm going to start with chapter 1 here, which is an introduction to the history of languages, and we'll start off with a Norwegian mathematician named Niels Abel. Abel was a mathematician that did a lot of work in abstract algebra back in the 1800s, earlier in the 1800s. There was a lot of work going on at that time in the area of abstract algebra, and there were computations that were getting more complex. And mathematicians, as a result, wanted a way of describing computation. They wanted a way of describing the different techniques that they were using for solving problems and proving theorems, and so they were looking for a language that would help them describe computation. Abel lived in the early 1800s, and he was followed closely by Sophus Lee, another Norwegian mathematician that picked up with a lot of the work that Abel did, but also was working in geometry, which was also a very big area at the time. And Sophus Lee combined abstract algebra and geometry to come up with what was called the Lee Algebras at the time. And these Lee algebras were very complex. It was there were lots and lots of operations that took place. Lee groups is another name for some of the work that he did, and there were lots and lots of calculations that had to be done, and it was very complex, and it was very hard for other mathematicians to verify Lee's results until computers came about that were capable of handling some of the calculations he was carrying out in the 1800s by hand, and the proof that these Lie groups were useful is in the fact that they're used now in developing aircraft for fluid dynamics and those kinds of things. Lie groups come up all over the place in the area of fluid dynamics. So there was a lot of work being done in the 1800s, very complex work, and there wasn't really a good way of describing the computation that went along with this work. Along came, in the early 1900s, a mathematician, Alonzo Church, who was interested in describing computation and came up with a language for describing computation called the Lambda Calculus. So using the Lambda Calculus, it's very, very simple language. He was able to describe lots of different kinds of computations, and he was working on some research that would say that the Lambda Calculus was sufficiently strong to describe any kind of computation that needed to be carried out. It was also very simple language, so trying to describe complex computations in the lambda calculus would be very difficult, but the point is that he was able to prove that he could carry out any kind of computation given enough time and enough energy to develop a lambda calculus for that problem. One of his students was Alan Turing, and Alan Turing is famous for many different reasons. He aided in World War II. There's been a movie made about him in cracking the Nazis' encryption machine that they had at the time. But he's also very famous in computer science because after he was a student of Alonzo Church's, but after he had left the university and had graduated, he started to develop a language for describing computation as well, and it was called the Turing machine. So the Turing machine description has a tape and a head that can move left or right, and a set of states that describe some computation using the tape to remember information as it's being computed. So it has both the input, the tape has both the input to the computation, and it can contain the output of the computation as well. So Alan Turing had been working on this Turing machine description and was proving that all computation could be carried out by a Turing machine. Alonzo Church at the same time was developing the lambda calculus, and he also was able to prove that all computation could be done using the lambda calculus, and the two of them then got back together when they found that they both had these papers about computation, and they came out with something called the Church-Turing thesis, which says that all computation can be computed with either the lambda calculus or a Turing machine, that the two models of computation are equivalent in their power. So they're different models of computation, but equivalent in their power. So Church-Turing thesis was a very important result very early on in computer science, that all computation could be described in either of these two forms. We'll come back to that later. So early on, we had computers that were being developed. The ENIAC computer is arguably the first computer that was developed, first electronic computer that was developed. Charles Babbage described a mechanical computer back in the 1800s that actually didn't get built until the late 1900s, but did work as Charles had described it was going to work. But the first electronic computer was either the ENIAC computer or the ABC computer. The ABC computer was developed at Iowa State. The ENIAC computer was being developed out east. ENIAC's purpose was to build tables for launching shells off of ships. There had to be trajectory tables that had to be computed. ENIAC was finished in 1945, right at the end of World War II, so it never really did serve its purpose. ENIAC was programmed by plugging cables into a switchboard, looked something like a telephone switchboard, and that was the program. And the data was stored in memory for ENIAC, and it would act on that data and then produce its result in some output form as well. So that was ENIAC, and again, ENIAC didn't live much past 1945 because there was another computer that was being developed about that time called EDVAC. The EDVAC computer was really kind of the first of the modern day computers. It was a stored program computer, which meant that the program, instead of being programmed by some other means, the program was actually stored in memory, in the memory of the computer, along with the data that the program was going to act on. This idea of a stored program computer was first proposed by John von Neumann in about 1945. So he came up with the design for a stored program computer, and that was used in the development of EDVAC. It wasn't long after that, about 1946, that Alan Turing wrote a paper about stored program computers. Alan Turing there again wrote a paper about stored program computers that was much more detailed than John von Neumann's, but we get the modern day computer. The name of the modern day computer really comes from John von Neumann. It's called the von Neumann Architecture. And the idea is that the program and the data are stored in the memory of the computer. And then the program is read out of the memory into the CPU. These are instructions that are being read, and the instructions tell the CPU how to act on the data. That design has been around since the very beginning, since about 1945. So, going back to a little bit of the history of computers here, we had this von Neumann architecture, but we've already described kind of two different ways of talking about computation. In the one sense, we have the Turing machine, which is a tape that can be read, and states that we have and transitions on those states. That's very much like the von Neumann architecture. The tape can be thought of as the memory, and the instructions are the states of this machine, and we're transitioning between different states. So similar in some sense to the von Neumann architecture a Turing machine is. The other model of computation is the Lambda Calculus, and the Lambda Calculus comes more out of mathematical understanding of computation, and so there were kind of these two competing different ways of thinking about computation at the time. So we had development of some programming languages pretty early on, and John Bacchus was responsible for developing one of the first modern programming languages called Algol 60. ALGOL, short for algorithm. So Algol 60 was designed with a grammar. The language had a grammar that was associated with it, and so there was a compiler for this language that could take the high-level language and convert it into a low-level language of the machine. And that conversion process was all driven by a programming language grammar. And John Bacchus was responsible for some of the definition of that language for describing the syntax of programming languages. So this way of describing the grammar of a language is often called BNF, or Bacchus-Naur format. And the Bacchus part is for John Bacchus, because he was instrumental in defining what this BNF format was going to look like. So Algol 60 was one of the very early programming languages that was being developed, and it was, I believe the definition of it started in about 57 or so, and it was about 1960 when Algol 60 became available. I talked about two different competing styles of programming, and Algol 60 is a member of that imperative von Neumann architecture style of programming. So that the Algol 60 is an example of that. John McCarthy here, about the same time, was working on more of the Lambda Calculus side of things, this other model of computation, and he was working on a programming language called Lisp. And he developed Lisp as an implementation of the Lambda Calculus, and that's a functional style of programming, much different than the imperative style of programming that is more closely associated with the von Neumann architecture. But he was able to implement Lisp as well early on, back in the 60s. He was able to get an implementation of Lisp going as well. Okay, so that brings us to our first practice problems, and there are a few problems here that you could certainly try to answer, and again, solutions for them are found at the end of the chapter in the text. So I want to go back and just talk about these different models of computation with a few pictures here for a moment. So I talked a little bit about the imperative model. The imperative model is based on that von Neumann architecture, where we have the program stored in memory and we have the data stored in memory. But to make things work in a computer program, we need to have that data structured in a certain sense. So we need some structure to the data. The program is stored out in memory in the imperative model, but the structure to the data is really these three pieces together. So we have a runtime stack. A runtime stack contains activation records, and each activation record represents one function that is in the process of executing. So every time a function is called in a program, we're going to push an activation record onto the stack, and every time a function returns, we're going to pop an activation record from the stack. Purpose of activation records are to store temporary information that is needed by the function as it executes to be able to remember its state. And primarily its purpose is when another function call is made, the state is stored for the current function is stored in this activation record. The other function executes, and when we return from the function and pop that activation record that we popped when we return, we restore the state of the current function from the activation record. So this stack of activation records keeps track of current state for each function that we're executing. The heap, on the other hand, the heap is responsible for storing all data that we're going to allocate dynamically while the program is running. So there may be pointers into the heap from the activation records. Everything would start in the activation records, but we may have pointers that are references that point to data that is in the heap. And again, the heap is responsible for holding any data that is created dynamically as the program is running. And every program might have some static data as well. The static data is typically constants and those kinds of things, and they would be there pretty much permanently throughout the execution of the program. So in the imperative model, we've got the program that's in memory. We've got a runtime stack, which is responsible for maintaining state of functions. The runtime stack has activation records on it, and an activation record is pushed when a function is called and popped when a function returns. And the heap is responsible for holding all of the dynamically allocated data, and static data is things that don't change as the program executes. Okay, so we got some practice problems here, but we're going to jump into functional languages. And all I would say about functional, I don't have any pictures to go along with it, but in the functional paradigm for Lisp and other things like that, we have exactly the same picture. So we have the program stored in memory as the program. We've got a runtime stack of activation records. We've got a heap area. We might have some static data. The only thing that's different in the functional model is that the program, the distinction between the program and other data is kind of minimized in the sense that the program is also data. So we can think of a program as data as well as being a program. We still have a runtime stack, we still have a heap, and we still have static data. Okay. So I talked about two paradigms of programming, the imperative paradigm, which is like the von Neumann architecture in a sense. We've got the functional style, which is a little bit more like the Lambda Calculus. There is a third style of programming as well. It's called the logic model. In the logic model, what we do is we write facts and rules about data, but we don't write a program, and that's because in the logic model there is one program that has been written called unification. So this unification program is out there that has been written by the implementers of Prologue. Prologue being the main language for logic programming. And what we do is we provide a database of rules that help control this other program. So we don't really write a program, but we write rules and facts that tell this other program how to execute. And that's the logic model. So I know that's very high level at this point, but you'll understand it much better later. Okay, so I wanted to talk a little bit about the origins of a few programming languages, and I thought I'd start with C++. Around 1972, Unix was being developed, and the Unix operating system, to implement the Unix operating system, a language called C was created by Kernighan and Ritchie. C was a great language because it allowed the programmer to get right down to the hardware and control very low-level kinds of operations in the hardware. This is exactly the kind of thing you need to be able to do with a operating system. You need to be able to get down to the hardware level, but it's still a high-level language, so it was very portable. You could take this code that was written in C and you could recompile it for different architectures pretty easily. So C was a great language, but there were other folks that were thinking about ways of organizing code, and they started thinking about organizing code around data, and this became the object-oriented programming style. Nicholas Wirth was experimenting with this object-oriented programming style, and he developed a language called Modula 2. There was also some other languages that were being developed about the same time or a little earlier. Simula was another language that was an object-oriented language, and Bjarne Stroustrup was working for Bell Labs around 1980 and was developing a follow-on to C called C++, the plus for the increment. So this was kind of in C incrementally better, but also backwards compatible with C. So Bjarne had in his head that he would like to develop a object-oriented C, but it had to be backwards compatible with C so that people didn't have to rewrite all of their C code. So this was the origins of C++. The first compilers came out in the 80s for C++, and there was a lot of excitement about it at the time, but it's also been a language that, while it's quite large, has been developing over the years. An ANSI committee took over the extensions or the new features of C++ that have been added back in the 90s. So there's been a C++ 98, and now there's been a C++ 2011. So Bjarne Stroustrup was where it all started from, and it continues development to this day, and it's a very powerful language, and it's also still backwards compatible with C. So lots of good things about C++. Python was started by Guido van Rossum, and it was started as a winter project back in the 90s. It's a little different than C++. C++ is a compiled language, which means that when you write a program in C++, you run it through a compiler to produce low-level machine language code for the computer that you're running on. Python is an interpreted language, different than a compiled language, because the interpreter is really the program that runs Python programs. So in a sense, what we're doing here is we're not writing a program anymore, a little bit like this logic model up here. There's a single program, it's called the interpreter, and we're writing rules that control that interpreter. But in this sense, these rules are imperative style, object-oriented style programming. So C++ and Python have some similarities because they're both imperative, object-oriented programming languages. But C++ is a compiled language, and Python is an interpreted language. In the late 1960s, there was a system called Logic for Computable Functions, and it was a theorem-proving system. And they were trying to come up with a way of describing the language of proving things within this system. And that was how Standard ML got developed. Standard ML was the language that was going to be used or was being used by this theorem proving system, the logic for computing computable functions, or LCF. So Robin Milner was working on this LCF system, and he was the one that designed this standard ML language and actually came up with a way of proving that standard ML had a very robust type inference system. So turns out that this type inference is very important for programming languages, because having a static type checking can catch many errors that programmers make while they're writing code. So standard ML came out of a theorem proving system. David McQueen has had some input on how standard ML was implemented. Mods Tofty is another person that has done some work with standard ML, but it became a standardized programming language. There have been a couple different specifications for standard ML, and it is one of the languages that we study within this text. Actually, about the same time, back in the 60s, the language of Prologue became of some interest also to people who were doing theorem proving kind of work. So Alain Comer was working on theorem proving, and actually was working on understanding natural language processing, the French language in this case. And he was trying to come up with a way of describing the grammar of languages. And it turns out that through his work with Robert Kowalski, Alain Comer and Robert Kowalski came up with a way of describing grammars through logic. So, and the language that they ended up designing as a part of all of this was Prologue. And it turned out that Prologue was a lot more important than just for natural language processing, but that is also one of the uses of it. So we have three different paradigms of programming. We have the imperative, object-oriented, that C++ and Python are members of. We have standard ML as an example of a functional language, and we have Prologue as an example of a logic language, and all of the folks here that have been instrumental in defining these languages. Every program that you write has to be translated into a low-level implementation that can be run by the CPU. This low-level implementation is in a language called the machine language of the machine, or the machine language of the CPU. And this machine language is just a bunch of zeros and ones and is not very interesting to look at. We certainly wouldn't want to program at that level. So the source programs like Python, C++, standard ML, Prologue, whatever the source language is, they have to be translated eventually into a machine language that can be understood by the CPU. Typically, programs go through some kind of intermediate representation on their way to being translated into this machine language. For compiled languages like C++, the source program is run through a tool called a compiler. The compiler consists of a parser. The parser is a program that takes the source program. Using a grammar that is defined for that language, it constructs what's called an AST, or abstract syntax tree. That abstract syntax tree runs through another piece of code called a code generator that translates the abstract syntax tree into assembly language. And the assembly language might be assembled with some kind of an assembler and translated into machine language, and this machine language is the language of the CPU. So that is how a C++ program gets translated into a machine language program that the CPU can execute. In an interpreted system, you notice here that the pink area is the machine language. That's what the CPU understands. In an interpreted language, the interpreter is already written in machine language. possibly having been compiled by using a compiler, but the interpreter is the thing that is in the machine language. So for Python, Python's interpreter is a machine language program. Now that machine language program reads a Python program as its input, internally builds an abstract syntax tree just like we did with the compiled version. Internally, there is a code generator that generates what are called bytecode instructions for the virtual machine. So the virtual machine has its own bytecodes that it understands, and it's these bytecode instructions that the interpreter actually executes. But each of these bytecode instructions is implemented as a bunch of machine language instructions that the CPU can understand. Okay, so that virtual machine in this case, this virtual machine is buried inside of Python, and this is, or inside of the interpreter, and this is how Python programs are executed. Sometimes that virtual machine is exposed to the real world. So in that case, we have the virtual machine, which is a machine language program again, but it's a separate program, separate from any other part of the system. This is more like how Java programs are executed. In a Java program, we take a source program, run it through the compiler, which produces an AST, runs through the code generator, which generates the bytecode instructions, but the bytecode instructions are stored as a separate file or files, and they happen to be, in the terms of Java, they are the .class files. So if you compile a Java program, you're going to see a bunch of .class files. That's the bytecode instructions for the virtual machine, the Java virtual machine. Java virtual machine, again, is a program, a machine language program that runs right on the CPU of the system. So this is kind of a hybrid implementation. It's not a compiled language per se, because Java is not a compiled language per se because it is not compiled directly to the machine language, but it is compiled to bytecode instructions. So Java programs are compiled, but they're compiled to bytecode. C++ programs are compiled directly to machine language, and Python programs are interpreted. Actually, the same goes for standard ML. Standard ML programs are interpreted as well, and Prologue programs are interpreted as well. So Prologue and standard ML fit under this interpretation umbrella here for the way they're implemented. Okay, so we've covered a lot of things in this first chapter pretty quickly. We've covered some of the history, some of the motivation for the development of programming languages. We've covered 3 paradigms of programming: the imperative object-oriented paradigm, the functional paradigm, and the logic paradigm. We've talked about some of the pioneers that were a part of these 3 paradigms of programming and some of the people that came even before them. And we've talked about 3 different ways of implementing programming languages, both the compiled version, the interpretation version, and kind of the hybrid version of both compiling and interpreting the program. So that should give you some good background. I'd encourage you to get the text again and read through chapter 1. It's covered in much more detail there. You'll learn some interesting tidbits about the history of languages, and also probably pick up a few details that I've left out within the lecture here. That's all until next time.